Okay, today's video I'm going to go ahead and do the together problems for chapter 12 for the very first homework assignment. So the first one that we're going to do is, if you need to, open your textbooks at the end of chapter 12, page 598. Okay, we're going to do number 17, number 18, 19, and 22. That's what we're going after today. Okay, so for number 17, what you have is a reaction. Okay, you have 4 giving us elemental phosphorus as well as 6 diatomic hydrogens. Okay, so what they're trying to find out, it says if in a certain experiment over a specific time period, 0.0048 moles of our reactant, so I'm just going to write this up here, 0.0048 moles, okay, is consumed in a 2.0 liter container each second of a reaction. What are the rates of production of the phosphorus and the hydrogen in this experiment? Okay, so they're telling us per second. And remember, your rate in general is going to be equal to your change in concentration over your change in time. So since it gave me 0.0048 moles, it also told me that it was in 2 liters. Okay, so my concentration is going to be 2.4 times 10 to the negative third moles per liters, and since they told me that it was per second, this is my rate. Okay, so this is my rate of consumption of the phosphorus trihydride. Okay, oops, there's that molecule right there. Now, what they're asking us for is what about the rate of production for the 2 products? Okay, so all that we have to do is look at the mole ratios on this one, simply because it doesn't give us another way with which to talk about, or not another way, but we can use that as a production ratio for this one as well. So since it's the 4 to the 6 and then the 1 on this one, if we look at the phosphorus, okay, the change in the concentration of the phosphorus per unit time, bring this down just a little bit, okay, is going to be equal to, now we're going to put this negative sign in front of it because we want to make it positive. Okay, you've got negative 1/4 of our concentration of our reactant. We've got it over delta T, which is going to be seconds. Okay, so in essence what we're going to do is take our 2.4 times 10 to the negative third. We're going to divide it by 4, and that's going to give us 6.0 times 10 to the fourth moles over liters times seconds. Okay, so that's my production rate for the phosphorus. Again, where did I get that from? Well, that's because I'm only going to generate 1 phosphorus for every 4 reactant moles that I have. And then for the change in the concentration of hydrogen gas, okay, and this is also delta T, but it told us it was 1 second, so it really just made the math easy in that respect. We're going to have a negative 6 to 4 ratio because we've got 6 hydrogens for every 4 there. So we got negative 6/4, and that's of our change of our initial reactant over delta T. So my 2.4 times 10 to the negative third, and we're going to take that and we're going to multiply it, however you want to say it, by 6/4. Now, I know we put the negative sign out here because it's going the opposite direction, but the typical commonality is to always give positive values for our changes in our rates. So that's why I put it out here and I kind of ignored it when I get here. It's kind of like thermo at the end when you just take stock and figure out what you're going to end up with. What should the sign be? And whenever we talk about rates, we almost make them positive. So that's going to give us 3.6 times 10 to the negative third, and again you've got moles over liters times seconds. Okay? Excuse me. Okay, so that's number 17. Now let's go ahead and do number 18, which is a very similar question. So for number 18, and you can find this video on eChalk if you need to go back and rewatch it, or pause it and kind of slow it down and do it that way. For number 18, we've got the Haber process. This is a pretty common reaction where we take nitrogen, we react it with oxygen, and we get ammonia, which is really important for agriculture because ammonia is a really common fertilizer. All we want to talk about is the relationship between the rate of production of ammonia and the rate of consumption of hydrogen. So what we're looking at here is these are the two that we're focused on, and this is going to seem super simple, at least I hope so. Okay, we're looking at nitrogen compared to hydrogen, and so regardless of how you want to manipulate it or look at it, your change in please don't show that message again. Your change in ammonia, okay, over delta T is simply going to be, and I'm going to put the negative sign out here again just to show you the not respect, but to show you the perspective how it changes. Negative 2/3 the value of the change in the concentration of hydrogen gas over the change in time. And again, that just simply came from the balanced chemical reactions, or the ratios and where those come from. So if it just talks about rate of production based on the ratios in your moles, you use your molar values to figure that out. Okay, let's do 19. Now 19 is a very important problem because if you remember from the video, I talked about the fact that lowercase k has very funky units, meaning that they will change depending on the order of the reaction and depending on what we end up with for our order of things. Okay, so if we look at 19, all we're going to do is establish the units. So if you are not sure on some of these things, you can refer back to number 19 and it's going to give you the units. Okay, so for letter A, it's simply the rate of a chemical reaction. So in other words, how fast does something change? And we can even go back to number 17. Every time we talked about a rate here, it was always the change in concentration over the time. So whenever you're simply talking about the rate, okay, the units are always going to be moles over liters, which represents the concentrations, times seconds. Now, I should put a little asterisk here that you can have other time units. Every once in a while, they'll like to throw you and give you minutes or hours or something like that, but it's typically going to be your concentration over your time. So since it's molarity, it's moles over liters times seconds. Okay. Now for letter B, it wants to know the rate constant for a zero order rate law. Now before I go any further, what that means, and again, you really need to watch these videos because this is new and it's different. You have the rate, which is going to be moles over liters times seconds. We're looking for the units for this lowercase k, and if it's zero order, I'm just going to pick A as a random reactant. We call it zero order, but when we do math, we raise it to the 0 power. So in essence, what happens is we multiply it by 1. Okay, so it doesn't necessarily change your units because k is going to be equal to the rate. So when it's zero order, okay, your units are going to be exactly as the same as they were in part A. It's going to be moles over liters times seconds, or again, whatever time unit that they give you. Okay, now what we're going to do is establish the units for first order, second order, and third order. So for first order, which is going to be letter C, what does that mean? Okay, so if it's first order, it means that you're going to have the rate is equal to K and some reactant with the concentration raised to the first power or first order when we talk about it from a kinetic standpoint. So if we think about units, I'm not even going to plug numbers in here. Remember, we're solving for K. This is what we're solving for. My rate units are moles over liters times seconds, and my concentration units are moles per liter. Now, if I have to get rid of moles per liter, well, I'm going to end up dividing by that number, which is going to allow me to cancel out the units on this side. And when I do that, it's also going to cancel out the units on this side. So what's going to happen is that my K value, the units, are going to be equal to seconds to the negative first, or 1 over s, or whatever time unit that you're dealing with. Okay, so it may be minutes to the negative first, or 1 over minutes, or 1 over hours, or something like that. So that's first order. Now, second order, again, tried to warn you the units are ugly. Just highlight this number so that you can come back to it. For a second order rate law, or letter D, what we're looking for here is now we still have the same basic premise of a equation, meaning that we're going to have the rate is equal to lowercase k. That's what we're solving for. Only this time you have a to the second order. So again, if we plug in units here for just a second, our rate is still moles over liters times seconds. We're solving for k, only now we're going to have moles over liters squared. Okay, so what's going to happen is if I have moles over liters squared and I need to cancel those out, to divide whatever numbers are in order to manipulate it, I'm going to have liters squared over moles squared, or however you want to do it. That's going to get rid of that one, get rid of that one. Well, when I come over here, and I'm going to draw this out the really long way just to show you, if I have liters squared, it's liters times liters. So one of the liters gets canceled out, but one is still left. And if I have moles squared, well, one of the moles cancels out. So that my unit for K, for second order, reactions becomes, okay, it becomes liters over moles times seconds. Okay, for second order, that's what it comes out to. And then if we do a third order one as well, and one of the ones in the book we did a fourth order, I believe, to take it just a little bit further. For letter E, if we have a third order reaction, we start with the same basic rate equation or rate law, which is rate is equal to k, only this time we're going to have a to the third power, or to the third order. So what we end up with for our rates, it's still moles over liters times seconds. We're still solving for k, and this time we have moles over liters cubed. Okay, so this time, again, if I flip it upside down, I'd have liters cubed over moles cubed in order to cross everything off and get it simplified. Then over here, I'm going to have liters cubed over moles cubed. Well, that's going to cancel out one of them and take it down to squared. This is going to cancel out one of them and take it down to second. It's seconds squared, however you want to say it. So that my unit for K, for a third order reaction, is going to be liters squared over moles squared times seconds, or whatever that time unit is, minutes, hours, whatever. So the ratio that you can kind of get, not ratio, but relationship, is that whatever order it is, your exponent on your liters and your moles is going to be one less than that. So third order is liters squared, moles squared times seconds. Second order is liters over moles times seconds. And zero order, well, sorry, first order rather, it's gone, so it's just 1 over s, or seconds minus 1. Okay? It's tricky. Again, just keep coming back to number 19 if you need to reflect on the fact of what causes those changes.